Hello everyone, this is Professor Ma and this is the sections on the log functions. Okay, so what we are going to do in these sections is look at definitional log functions, introducing the two different type of logs we use the most, the ones that are on your calculator, the common log and the natural log. Then we're going to look at log equations and the simple ones. Then we look at finally at the rules for logarithms. So we start out with the exponential. When we take the exponential functions and like we take 4 raised to the third power, and the emphasis in this particular expression is if I take the base 4 and multiply itself 3 times raised to the third power, the output is 64. Okay, so this is the exponential formula. And in terms of what we have in terms of functions and inverse functions from last section, this is saying that this formula 4 to the third power, we're taking the number x equal to 3 and raised the formula 4 raised to the x power, in this case 3, and then it lands up to be the output 64. And this function has an inverse function, and the inverse function takes 64, and so that function we call log of 64. Okay, and what does it give? Well, it gives you the answer what exponents it's going to be. It's going to be 3. In particular, because base is 4, and that's what we're going to put the little 4 there to indicating this associated with base 4, because there are a lot of different other bases. Okay, and basically that's it. That's a loop. The log is the inverse of the exponential formula. So in particular, so in other words, if I'm interested in what exponents I need for the base 4 to obtain output 64, so I know 64. So what is the x was used for the exponents? That number I call log. Okay, so log base 4, we write it as log, and 4 is, again, what's the base I'm using is very important. It's the size of the units, if you like. And then we say this log of in base 4 of the number 64 is 3, the exponents needed. The reason we want to say that is because we want to emphasize the different parties in the context, just like Bart studies Homer. Okay, it contains exactly the same information as saying Homer's son is Bart. So these two expressions contain exactly the same information. 64 is 4 to the third power, or log base 4 of 64, or 64 a log 4 of 64 is 3. The exponent is 3. And this form is called exponential form. The other equivalent forms having the same meaning, looks different, we call that the log form. Okay, so in this type of situation, we have the option to express the relationship in one format or the other format. Okay. And so here's the general definitions of what we mean by log base b of something is x. Okay, if b raised base b raised to x is y. It's the inverse functions of the exponential b to the x. Okay, so let's do some practice. The most important things when we to convert is convert the practice converting between the form until we get used to it, and then when we read the log expression, the first things we should recognize is zooming on is what's the base we're using. So hence, here are some problem in exponential form, and convert them into the log form. Then for the first one, it got to be log base equal to 4, and then the next one is log base 2, 8. The next one is log base 2. Okay, so we must have the different size of log on the side, 4, 8, and 2. Okay. Again, those are just like little tags tell you what base we are working with. It's like the size, the shoe size tag is a size number 9. So we have number 9, and then it will come in handy when we convert things into some other form, into the exponential form. Okay. The 64 is the output, and what's exponents used? And then respectively is 3 and 2, and to get us 2 raised to 6 power. So I need 6. Okay. Note one thing. In order to log some numbers like 64 here, it got to be positive, because these are all positive output from exponents. So I must have all positive number over here. Okay. On the other hand, I might get negative answers. So for example, if I were to switch this problem to log, flip every one of them around, like for instance, if I'm talking about log base 4 of 164, then the answer will be negative 3. Okay. And the same thing, if I was log base 2 of 164, then the answer will be minus 6. Negative means it's reciprocated. Okay, and so the domain has to be, for the log function, has to be positive number. This doesn't make sense. The calculator will say it's invalid. Okay. So here's the step-by-step conversions. So this is just like rearranging blocks B and X and Y from one form into another form. So here is the exponential form. I'm going to put into log form. First thing, the base, log in the base B. Okay. First thing, go for the base. Then the output Y, then the X is the exponents. Okay. This is the inverse loop, taking power, taking log. So here are some examples. Base 4 of 16 is 2. Base U of W is power e to plus V. And this is how we do it the other way, from log, go back to exponential form. Put the base down first again, and X the power goes on top, should give us the Y. So these are the respectively the conversions into exponential form. Okay. So yeah. So here are some examples you can write from one form to the other form. Now, what basis we got? Any number can be used as base as long as it's positive. So what basis do we use the most? Well, we use the following 3 bases the most: 10 to the x. Okay, the 3 bases that we use the most: 10 to the x, e to the x, and 2 to the x. 2 to the x is mainly in computer science. Okay, and these are in science and biology, accounting, business. And the base 10, we call that the common log, because 10 is the common unit. So usually on computer, we don't write it, the base 10. The 10 is not there. So if you look at your computers or calculators or on a cell phone, usually log, log, no base, it's base 10. And The other base, of course, is the base E, the one, remember the Pareto formula for compound interest, continuous compound interest, and that's used. So on that, we write as natural log, Ln. So Ln is the same thing as log with base E. Okay. So we have these two bases, and here is exercise converting back and forth using log or Ln. So in the log form is log, and so in exponential form that must be E, base E raised to the second power minus second is 1 over E. And so these are the conversions. I'll let you ponder over it. Okay. Now, again, we said that the log and the exponential taking power, they form an inverse pair. So here's 50. We're going to feed 50 into log. Okay, log base 10. Let me just emphasize. I'm going to get a number. Okay. And how do I get back to the 50? The original number I fed in. I take this number, I raise it to the power. Okay, put it on as the power because that's what log of 10 is. This is the log of the x. This number I get, that's what log of x is. Then when I put this number up here, that output should be 50, and this is a round trip. And so look at as below. If I log 50 is 1.69, blah blah, and I raise 10 raised to the power base 10. And if you punch it in, I almost get 50. The difference is the roundoff error because computers only calculate so many digits, and these are supposed to be infinite many digits. Okay, so this is the one round trip. So you can, there are more examples here using base E and Ln back and forth. Okay, yeah. So these are more demonstrations of the inverse pairs between the log and exponential functions, common logs and base 10. Okay. So we can make equations up just to make sure that people can remember how to change one format into another format. And then we're throwing an X in there. Then it says change the format into another form, turns into equations. And what type of equations? First degree, second degree. That's it. Or something can be turned into first and second degree. Okay, a fractional equation that can be turned into first or second degree equations. Like this one. Okay, and this is this is a second degree equation. After I put into the base x, and this is 1 over x squared, it's 9, and then per denominator, I get 2 answers. Only one is valid because x has to be positive, so the answer is 1/3. So this is how we can create equation by putting an x in particular positions in the symbol. So you have to solve, and again, first or second degree equations. Here's a picture of the log functions. We fill in the log if you want to plot the points, and we get this curve. Okay, and yeah. Oh, notice there's nothing on the left-hand side because x cannot be negative. Okay. So here is, if the base is less than 1, then we'll have the log goes the other way. Now we come to the rules of logs, and log basically to do with exponents. So the rules in exponents, multiply, add, divide, subtract, taking power to power, multiply. Those rules for exponent translate into rules for log, and do the same things. Multiply, add. When we log the product, it becomes additions of the log. Log of quotients become subtractions of the log. Divide, subtract, multiply, add. Power to a power, you can take the power comes out. This rule. This is basically rephrasing each part of the rule carefully into language of log. So here's one proof. I'm going to leave up for you to read to sort it out. Okay, so who plays which role? So therefore, the rule can be reinterpreted into the right-hand side into the log form on the right-hand side. Okay. So now, how do we do? What do we do with these rules? So one of the things we do with this rule is we can take log of a complicated formula that's made up with multiplications and power and divisions. We can break it up into individual logs. Oh, okay. First, write radical as power. Of course, I need to use the power rule. And this is a division, so therefore I can write this as difference of 2 the top versus the bottom. The front is a product, therefore I can write as log of 3 into 2 parts plus log of x squared, but that's one thing times the other. And the back one, the exponent 1/2 can come out to the front, is minus 1/2 log of y. And then finally the 2 can come out to the front of here, so it becomes 2 log x. Okay, so we have this, and this is everything stripped apart. Okay. Now I can put everything together. Okay. For instance, 3 times log of x. This 3 I can interpret as the same as log of the x to the 3rd power. That's what we mean by this exponent can go in the argument as power or multiple constants outside. So next, we're going to put all this now back into a compact form, into one log. Okay, and how do we do that? First, we pack all the exponents back into the argument. So x, this is the same as log of x squared, and minus 1/2, we can put the exponent 1/2 back into the further powers of y. So I will have the following. Now, log of something plus log of something else, this is the product, the log of their product. Therefore, I can condense into log of these 2 items multiplied together. Of course, I still have minus log of these 2 contaminants. But log of subtraction is dividing, it's the same as log of a quotient. The one in the front goes on top, minus becomes the divided by, as it is the minus becomes division. And this becomes one compact fraction, and the log, we have log of these fractions is the subtractions. Okay, that's a quotient rule. So these three rules of multiply, add, and divide, subtract, powers becomes multiplications. It's are the fundamental rules for exponents. And anywhere you see these type of rules, it always comes down to basically has something to do with exponents. Again, log and exponential are inverse functions. So therefore, if I raise minus 2 to the minus 5, then log with 2, I'll get back the original minus 5. And the same thing, if I log xy, and that's the exponents, and then raise a to the exponents, the same base, I get back xy. It's a round trip. This one, we use the addition rule. Exponents added, actually is multiplications. Okay, to get addition of the exponents, then e to the log 7 is 7. So then 7 is 4. Okay, that's it. Bye-bye. Until next time.